We've begun chapter 6, which is our first look at polynomial congruences.
Yeah.
Okay. So just to summarize, the basic task here is solving problems like this. Okay. F of x congruent to 0 modulo n, where f of x is a polynomial with integer coefficients. We're not talking about things, because we're doing number theory here in modular arithmetic, so everything has to be integers. So f of x is a polynomial with integer coefficients. Okay. Whenever I say the word polynomial, in this unit, it's polynomial with integer coefficients. I'm never gonna say it again. Okay. Now the easiest case of such things to look at, not really, not full-blown polynomials, but a starting case to look at is linear order 1 polynomials, the linear congruences, i.e. polys of order 1. Order 1 means the largest power of x that appears in the polynomial is just x itself, x to the power 1. So these look like, i.e. problems like ax congruent to ax minus b congruent to 0 modulo n, or ax congruent to b modulo n. Okay? So we're trying to solve these things. A couple of, and we proved a couple of results about these so far. Remember, when we say we're looking for solutions to this, we're looking not just individual integers x that solve it. Really, you regard the solutions of this as being certain of the congruence classes modulo n. Okay? Because if one particular integer x solves this, then so does any other integer that's congruent to x modulo n. Okay? Because if something else is congruent to x modulo n, then when you multiply it by a, subtract b, you'll again be congruent to 0 modulo n. Okay? So the solutions we're looking for are congruence classes modulo n. So quickly going through, just reminding ourselves of the results we proved yesterday. Theorem 6.1, if the GCD of a and n was 1, if a and n are coprime, it's the nicest situation. It means there's a single unique solution. The point there is, i.e. a inverse modulo n exists. So a single unique solution, which is x is congruent to a inverse b modulo n. Okay? If a and n are coprime, a does have a multiplicative inverse modulo n. So you multiply both sides by a, that'll cancel the a from this side and leave you with the a inverse times b on the other side. Okay? So if the coefficient of x is coprime to the modulus, then there's a single unique solution. That's more or less proof of it there. Okay, that's fine, but what if it isn't coprime? If the GCD of a and n, okay, what about in general, for general GCDs? Well, we proved yesterday there are solutions, then solutions exist if and only if d divides b. Okay. If the b part of the constant coefficient is divisible by that greatest common divisor d, then there will be solutions or solutions to the polynomial. If d does not divide b, then there won't be. Okay. So we've got a criteria or a criterion for the existence of solutions. That criterion or test is you work out the GCD of a and n. You work out the GCD of a and n, you get this number d, and you test Does D divide B? If it does, then there are solutions that can be found. If it doesn't, there are no solutions. Okay? So we proved that yesterday. So where we want to pick up the story then is into theorem 6.3, which completes the story and describes, well, if D does divide B, then what are the solutions? How many solutions are there, and how can we generate? We need a formula or some kind of constructive method that's going to lay out what the solutions are. Okay? So this is in the notes. I think I'll talk to the proof as it appears in the notes rather than writing it out as we go along. So we'll look at the proof in the notes now. I might come back here and make a few remarks here as we go. So let's look at the statement. Okay, so this is continuing the story from theorem 6.2. We're considering a linear congruence, AX congruent to B. And we're assuming that there are solutions. So the GCD of A and N, this number D, it does divide B. And here in equation 6.15, we've got the precise description of what the solutions are. The solutions, there's D of them, and they're indexed by this index I, by this parameter I, and I runs through values 0 through D minus 1. So there are D possible values for I. And it's telling us what the solutions are. Each of the solutions is T plus I times N over D. Now we know what N and D are. N is the modulus in question. D is the greatest common divisor of A and N. I is this parameter, which is going through those values. So what's T? Well, T is the single unique solution that there is, modulo N over D, to what we call the reduced congruence. Okay? So we take our original congruence and we reduce it by dividing each part of it by D. Remember, these are just, though they look like fractions, but they are integers, okay, because D divides each of these numbers. D is a common divisor of A and N, and we've assumed further that D divides B. So these are actually all integers here. So we look at this reduced congruence, and T is the single unique solution to that. Okay? So you reduce the congruence, find the solution to it, and then feed it into this pattern here, where you take these various values for the parameter I. Okay? So let's look at the proof of that. And then after we look at the proof of it, we'll start using it in some examples to make sure we understand it and know how to implement it. Okay. So where possible, we always like to make use of previous results. Okay. So back in the chapter on congruences, when we introduced the congruence relation, we said that if a number here D, if a number D divides all three parts of a congruence, the left-hand side, the right-hand side, and the modulus itself, then the first congruence is going to be true if and only if the second one is true. So we make use of that here. So that was theorem 4.4. Okay. So if AX is congruent to B modulo N, that's true if and only if A over D times X is congruent to B over D modulo N over D. Well, what kind of a congruence is this we're looking at? This is again a linear congruence. It's something times X, congruent to something, modulo certain modulus. But it's one of the ones it's the nicest type of one that's covered by theorem 6.1, okay? Because we've divided out A and N by their greatest common divisor. So that means the numbers that are left behind, A over D and N over D. So note here, A over D and N over D are coprime. They can't share any common factors because we've already divided them both by their greatest common divisor. Divided A and N by the greatest common divisor. So AD and N over D are coprime. So that means A over D has a multiplicative inverse modulo N over D, just as we talked about in theorem 6.1. You can multiply both sides by its inverse. So this will have a unique solution modulo n over d. So this, meaning this second congruence, has a unique solution. A unique solution T modulo n over d. Okay, so one unique congruence class modulo n over d, which is the solution. And we're going to let T be the standard representative of that congruence class. Now, all of the integers that are named in the theorem, I'll just repeat it up here so we can see it. T plus I times n over d, where I goes from 0, 1 through d minus 1. If T is the solution of this, then all of these numbers are in the same congruence class modulo T, for the same congruence class as T modulo n over d. Because you're adding on multiples of n over d onto T. Okay? So all of these numbers also satisfy this congruence here, okay? Because they're equivalent to T modulo n over d. So T solves it, so does anything congruent to T. So that's the point that's made there. The integers referred to in 6.15, namely these ones here, are all solutions of the reduced congruence. And hence of the original congruence, all those integers. So all of these integers here are possibilities for x. They're all solutions of the original congruence. So that's the point we reach at the end of that sentence there. All of these numbers are solutions of this. But that's not the end of the story. We have to tidy up a few points. So this bunch of integers are all solutions of this. So there's two things we have to do now. We want to prove that these are all genuinely different solutions of this congruence. Namely that all these numbers here, and there are d of them, all these numbers here represent different congruence classes modulo n. Because we don't want to repeat solutions. We don't want to, just name solutions multiple times. It's wasteful and misleading. So we want to know that all these solutions are all actually different. So we want to show that they represent different congruence classes modulo n. First thing we want to do about them. And the second thing we want to do about them is say that they're a complete set of solutions. We haven't omitted or missed off any other possible solutions to this. Okay? So the proof is working by, here's a bunch of numbers, a bunch of integers that solve this. Okay, we proved that up to the end of this sentence here. Here's a bunch of numbers that solve it. And now we're going to solidify a couple of things. We're going to prove that these should all be regarded as genuinely different solutions of this. So they all come from different congruence classes modulo n. They all come from the same congruence class modulo n over d. They're all T plus a multiple of n over d. But they're different congruence classes modulo n. And they're a complete set of solutions. And there isn't anything else, any other congruence class modulo n that solves this. So those are the two things that remain to be proved. So the first part is proved here. These solutions are all incongruent modulo n. Right? They're all different congruence classes. None of them are congruent to one. So we do that by a quick, well, it's kind of like a proof by contradiction. So yeah, so we suppose this was not the case. So suppose it wasn't true that these were all distinct modulo n. Well, if that was the case, if that wasn't the case, then we could pick out two of them that were congruent. Okay. So T plus R n over d and T plus S n over d would be congruent to one another, where R and S are two of the indexes I. Okay. So R and S are two of the numbers between 0 and d minus 1. Now we can subtract T from both sides of that congruence, leaving us with the congruence R times n over d is congruent to S times n over d. And then we can apply theorem 4.3. So theorem 4.3 told us how to cancel. See, we've got this common factor n over d, and I'd like to cancel it from both sides of the congruence. Okay? So we need to temporarily look back at theorem 4.3, which tells us how to cancel common factors from congruences. Theorem 4.3. How do you cancel common factors from both sides of a congruence? Well, here's this kind of setup. X times c congruent to y times c modulo n. Yeah, you can get rid of the c from both sides, but you have to adapt the modulus. That's what we do. So you can get rid of the c, but you need a new modulus, which is n divided by d, where d is the greatest common divisor of c and the modulus n. Okay? So in particular, if c is co-prime to n, that means d is 1. So that means you keep the same modulus, and you can cancel the c from both sides. So that's because if c is co-prime to n, it means c has a multiplicative inverse. So you can affect the cancelling by multiplying both sides by that multiplicative inverse, so you keep the same modulus n. But in general, you can cancel the common factor, but you need to adapt the modulus by dividing it by d, which is the greatest common divisor, the number you're dividing by, and the modulus. So we apply that now at the point that we're at here. So I want to cancel n over d from both sides. Now, what is the greatest common divisor of the pair n over d and n? What's the largest number that divides into n over d and also divides into n? Well, that is n over d itself. Okay. Remember, d is a divisor of n. So when you divide n by d, you get some integer, and that's still a factor of n. Okay? Because n is equal to n over d multiplied by d. So the GCD of n over d and n is equal to n over d. So that's the greatest common divisor. So I can cancel this factor from both sides, but I have to divide the modulus by that greatest common divisor. When you divide n by n over d, you're left with d. Okay. The modulus divided by this greatest common divisor leaves us with the modulus d. So if we assume that these two solutions were congruent to each other modulo n, we end up with saying that r is congruent to s modulo d. Now, R and S were two instances of the index I. This index I at the top, which ran from 0 to d minus 1. So R and S are between 0 and d minus 1. Now, what does it mean to say that R and S are congruent modulo d? That means that d divides the difference R minus S. It's the meaning of congruence. But if R and S are between 0 and d minus 1, that means the biggest distance they can be apart is distance d minus 1. Okay? You've got two integers trapped between 0 and d minus 1. The furthest apart they can be is d minus 1. Okay? Because they're inside an interval of length d minus 1. Yeah? So how can d divide r minus s then? The only way it can do that is if r minus s is 0. Because r minus s can't get to d or 2d or a high multiple of d, because it's trapped between the value 0 and d minus 1. So the only way that d can divide this is if actually r minus s is 0. So in other words, r and s are both the same. So this wasn't two different solutions here that were congruent. We simply just wrote down two copies of exactly the same solution here. Yeah, literally took the same expression twice. Okay. So it's impossible to have two different solutions here that we put up here that are congruent to each other modulo n. Okay. So that settles the first of our tasks that I outlined a few minutes ago. All of these solutions here We've already established their solutions of the linear congruence. They're all different solutions. Yeah. None of them are congruent to any of the others modulo n. So the only thing we have to need to settle about them is that we haven't missed any solutions out. Okay. So that's settled in the final part of the proof here. The final part of the proof is to show that those solutions are all of the solutions. We haven't missed any out. So how are we going to do that? Well, what we do is we suppose that there is one that we've missed out. Or we just imagine a general solution. So we think of this general solution S of this thing. So S is something you can put in for X that solves that problem. Well, we already know one solution, namely T, the solution we're using to generate all the other ones. So if S and T both solve this, that means that AT is congruent to AS. Okay? Because both of them are congruent to B, modulo n. So each of them is congruent to the other. And again, using theorem 4.3, we can cancel that common factor A from both sides. Okay, we can get rid of the A from both sides as long as we divide the modulus by the GCD of A and N. The GCD of A and N is already named here. This is the quantity D. So we now know that T is congruent to Y modulo N over D. And that means that N over D divides the difference, T minus Y. Or equivalently, Y can be written as T plus some multiple N over D. So Y is equal to T plus some multiple Q, say, of N over D. But this is beginning to look awfully like one of the solutions we wrote down at the top. Our collection of solutions T plus I times N over D. Here's one that looks kind of similar, T plus Q N over D. Now we don't know what the Q is, right? We don't know what the Q is. But we do know that we had a kind of complete set of representatives of all the congruence classes modulo D here. The index I ran through all the possibilities 0 through D minus 1. So Q is congruent modulo D to one of those. Okay. And if Q is congruent to I modulo D, that means Q times N over D is going to be congruent to I times N over D modulo N. Okay. We get that simply by multiplying all parts of the congruence through by N over D. Okay, so knowing that Q is congruent to I modulo D, we multiply through by the quantity N over D, all three parts of the congruence, and we get to Q times N over D congruent to I N over D modulo N. And then you can reintroduce the T if you want. So T plus Q N over D is congruent to T plus I N over D. T plus Q N over D will be congruent to T plus I N over D mod N. Primary school sometimes. Probably engineers. Right. Where was that? Where? So sugar. Sorry, did nobody put me up on this? Why did I suddenly replace S with Y? That's the danger of using the notes. Sorry, so, oops. S became Y here. So by mistake, I started typing Y for S. So actually, the easiest way to fix it is just correct that, the initial S, make that a Y.
From where?
From
all the way through. S is all the way through, yeah.
Yeah, but it's always referred to as Y all the
No,
way
but
through.
it's above it because you've got the R in there. Unless it's that.
Oh no, those are different R's and S's up there.
So from where you want to...
So from here,
That's really nice that we have.
Suppose that Y is any solution.
so yeah, suppose a Y is any solution of this, then AT is congruent to AY. Yeah. Pardon me
Probably
for
why
that.
you start using Y.
Yeah, probably to distinguish. Yeah, because I
you've
should
got S
do.
further up.
If I just, yeah. Now then we were starting a different argument, so it would be okay, you know, to kind of restart a different argument here. But it's probably good practice not in the middle of the same proof to avoid using the same letters. Yeah.
It's a big house.
Yeah. So that achieves. So this means that this solution Y that we thought about here. The solution Y that we thought about here is not something that we haven't listed already. It is congruent to one of the T plus I times N over D. So it is listed in these D solutions that we listed out originally. So that finishes the theorem. Okay. So the theorem was proved by first saying, look, this bunch of numbers are solutions to this. This bunch of integers are solutions to it. They all come from different congruence classes modulo n, and nothing has been missed out. Every solution of this linear congruence is congruent to one of these. So then you know that that's the complete story for the solutions. Okay. So that's the proof, but that's the general argument. Should definitely study that and understand how the logic is working through all the parts of it. But let's see it in action, okay? So with that theorem now we completely understand linear congruences. So given any linear congruence that someone throws at us, we should completely just be able to completely sort it out. Okay? So we could look at example 6.3. So there's a couple of worked examples here, and then we can move on into the exercise of 6.1. So question 1, 5x congruent to 3 modulo 24. How do we treat that? What observations do we make there? Okay, yeah, that's the meaning of the congruence relation. But looking at the three theorems we've proved. Yeah.
Can you say that the GCD of A and N is 1?
Yeah. So the first question to ask is, look at the coefficient of x, that's your A. Compare it with the modulus, and look at what the GCD is. Here we find it's one of the nicest ones, okay? Because that GCD is 1. Of course, 5 is a prime. 24 is not a multiple of 5. So that means we can use 5 inverse modulo 24 to get the single unique solution. To get the unique solution, single uniqueness. Or to let me say something twice. Whatever it is. To get the unique solution mod 24 to this. And it will be x is congruent to 5 inverse times 3 mod 24. Now what does that inverse happen to be? 5. 5, exactly. 5 is self-inverse. 5 times 5 is 25, just congruent to 1. So it's 5 times 3. And what does 5 times 3 happen to be? 3. Okay, so there's our unique, and there's no need to further reduce it to a standard representative because it's already reduced modulo 20. So there's our solution. You can check it out if you want. What's 5 times 15? It's 75. 75. Well, if you bring the 3 over the other side, subtract 3, you get 72. Is 72 congruent to 0 modulo 24? Yeah, it is. It's 3 times 24. Okay. So it checks out. So what was I using there? I was using by theorem 6.4. It's okay. Any questions? So 15 is an integer solution to this. Any other integer solution you might find will always be congruent to 15 modulo 24. It has to be. This x has to be congruent to 15. We look at question 2. This time we're looking at 25x congruent to 15 mod 120. So at first, there may or may not be solutions. Are there solutions? Well, by theorem 6.2, you answer that question by inspecting the GCD. 25 and 120, which is 5. Okay. 5 is the greatest common divisor. So you check the criterion. Does 5 divide the b, the constant? Does. 5 does divide 15, so there are solutions. By theorem 6.2. Theorem 6.2 says there are solutions. How many of them are there? There are 5. Okay, that 5 is our D. That's our D that we mentioned. Greatest common divisor of A and N. So my theorem 6.3, there are 5 such solutions. And these are given by, so these congruence classes, T plus I times, okay, N over D, what's that? So the N is the original modulus. D is that D5 there. So divided by, what's that? 12 to 14. So it's T plus various multiples of 14 modulo 120. And what are the possibilities for I? I is the 5 possibilities from 0 up to 5 up to D minus 1. Okay. So there are 5 solutions to this given by these congruence classes. 24. Sorry, excuse me, 24. Thank you. Sorry. Okay, so those are the solutions. Okay, so what is T? Okay, we know the possibilities for I, we know 24. What is T? So where T is the unique solution, to the reduced congruence, so what you do, you take the original congruence and you divide all the bits of it by D, which is 5 here. So that's 5x congruent to 3 modulo 24. Which by miracle is the previous one we just solved, isn't it? Yeah? Unless I said it was 14, yeah. So i.e. T is equal to 15. Okay? Good question. So the solutions are solutions to 25x congruent to 15 mod 120 are x congruent to 15. That's where I is 0. And you just keep adding multiples of 24. 39. 63. 87.
I think
24.
too much.
To the original t.
Okay.
Yeah? 111. Would I go one further? What if I did? 24. Is 135 not another solution? Why not?
Because it's supposed to be 25.
Yeah, so it is a solution, but it's not a genuinely new one because remember, we're talking modulo 120. 135, you're back at the beginning again. You're back to 15 modulo 120. So that's just illustrates that position. We only go up, we only follow the index I to 0. So this is I equals 0, I equals 1, I equals 2, I equals 3, I equals 4. If we did go one step too far, well, we're just back at the beginning again. So this is already listed. It's a different integer that solves it, certainly, but it's not a different congruence, guys. And having already listed 15, we already know anything congruent to 15 will be another integer solution of that. We know that. We're not interested in repeatedly listing equivalent integers. That's all. But these 5 integers here, these are all different modulo 120, and they are all solutions of this problem. Okay. Shall we do another one? Or any questions about how I laid that out? And
Excuse me.
yes.
You know here you said 5 inverse multiply 3.
Yeah.
And you said this is congruent to 5 multiply 3. Why?
Why? So back here, that was because what is 5 inverse? This is 5 inverse modulo 24. So that happens to be 5. 5 is self-inverse modulo 24. 5 by 5 is 25, which is congruent to 1 modulo 24. Always remember, the inverse is the thing you multiply by something else to make it 1. In general, but in this context, it's the other integer that you multiply by 5 to give you something congruent to 1 modulo whatever the modulus happens to be. Yeah, so 5, the inverse of 5 modulo 24 happens to be 5 itself. Okay, in general, the inverse will be a
1 over 5.
yeah, but that's the inverse in a different system, in the system of real numbers under multiplication.
So what is it in there?
This is the inverse under multiplication modulo 24, which has strong connections to regular multiplication, but it's strictly speaking a different operation. So it's operating on in a different domain. It's operating on the congruence classes modulo 24. So there are connections and similarities between, you know, the inverse of an element and the reciprocal, which is what you just named, 1 over 5. So you definitely don't think of it, it's not something completely different, but they're not the same. And we're in a different context here. So when we're in a modular arithmetic setting, the inverses we're talking about are not the fractions 1 over 5. Because that belongs to another context. The appropriate inverse elements here we're talking about is the other integer, the other congruence class, and when you multiply it by this, you get back to the congruence class of 1. Now 5 is one of these special ones where 5 mod 24, it is its own inverse. Typically, an inverse element will be a different element, but it can sometimes be the same element itself.
What is 6 inverse?
Well, okay, that's a good question. So what is the inverse of 6 modulo 24? Just to further explore. It doesn't exist. Because there's a criteria for the existence of inverses, which is that the GCD of the number and the modulus has to be 1.
Okay.
Co-prime.
Yes, because that's not the, yeah.
Yeah, 6 and 24 aren't above 20. Okay? Okay. So let's do one more to finish it off. Let's see, let's pick one, let's pick one, let's pick one. Just pick one at random. Go for question 7. Exercise is 6.1. Question 7. Okay. Okay, so our initial thought is this may or may not have solutions. Remember?
What is inverse of?
Okay, shh, please. There's a lot of chapter there. Yes.
What's inverse of 7 modulo
7.
7 is another example that's self-inverse. 7 times 7 is 49, which is congruent to 1 modulo 24.
Yeah.
So for this one, our initial question is, are there solutions? We assess that by working at GCD. This is what we're not sure. We could launch into Euclidean algorithm, or there's a relatively small, we might look instead at prime factorizations. 34 is 2 times 17. 98 is what? 2 times 49. 2 times 7 squared. So what's the GCD? 2. Yeah. Comparing the 2 prime factorizations, the overlap is 2. So the GCD is 2, and 2 does divide 6. So there are solutions. 2 solutions. Okay. To get the solutions, you first have to find the t. There's a lot of chatter there. Let's keep a lid on it. So to find the t, you look at the reduced congruence. You reduce everything by 2. But there we'll need the inverse of 17 modulo 49. If anybody can get that, I'll be impressed. Off the top of their heads. So let's get that from the computer. Stage cell.
Inverse of 17
Mod 49. This doesn't have it. Oh yeah, it does. I think it's inverse mod. Yes. Inverse mod 17. 39.
49.
How did you do that?
No, I think it's
Oh, it's 49. 26 apparently. Okay. So 17 inverse is 26 modulo 49. So we took that from Sage. So the command was inverse mod. There's multiple ways of getting it. You can run the Euclidean algorithm, find the linear combination of 17 and 49 equal to 1. And whatever the coefficient of 17 is, that's a representative of the inverse. Or you can raise 17 to the power of phi of 49 minus 1. What is phi of 49? You can evaluate phi of 49 from its prime factorization. You reduce the exponent on each of the primes by 1, and you multiply by 1 less than each of the primes. So that will be 7 times 6, which is 42. No, sorry, that's 98. Sorry, 49 is 7. I was just mentioning quickly multiple ways to find this 26.
Oh, okay.
7 squared, so will be 7 times 6, 42. Yeah, 42. So you could raise 17 to the power of 41. But that's probably a more difficult computation. So probably a quicker way is to run the quickest way is to ask Sage, or run the Euclidean algorithm, get the linear combination of 17 and 49 congruent to 1, and you will find that the coefficient of 17 in that linear combination, it might be 26 or it might be something else congruent to 26, modulo 49. But that's what it is. So T, our unique solution, is something congruent to 26 times 30, which is, anybody calculated 26 times 30? $780. And what is that modulo 49? Let me see. And mod 780 49. $45. Okay. So the two solutions that there are to the original question. So the solutions to 34x congruent to 60 mod 98 are any x congruent to 45 or 45 plus t plus I n over d. What am I supposed to be doing here? 45 plus 49, which is what? 99? 45, what did I just say? 45 plus 49, 94, 94. My brain was grinding to a halt there. Those are the two congruence classes which solve that.
How did you find them? You doubled the...
I doubled it, yeah. No, I did 40, because remember it's t plus I n over d. So that's 45 plus I, the n over d here, the n was 98, the d was 2, so it's 49, and there was two options for the I, 0 and 1. So it's my 45 and 45 plus 49. So like that's the whole story about linear congruences, really. There's nothing more to say. We now completely understand those.